Have you ever really stopped to think about the incredible device at the heart of medical imaging? It's sitting inside every CT scanner, every mammography unit, every single cath lab. On the outside, it looks like a simple sealed glass tube. But inside? Inside, it's a world of extreme physics. We're talking about a device that harnesses lethal voltages and temperatures hotter than the surface of some stars, all to perform a kind of modern magic, letting us see right inside the human body without ever making an incision. So let's peel back the layers and really dig into the physics that makes this all possible.
At its core, an X-ray tube is really just a particle accelerator in miniature. It's this precision-engineered system designed for one specific job: to take raw electrical power and transform it into a highly controlled beam of diagnostic radiation. But how does it actually do that? How do you get from a simple plug in the wall to a detailed image of a bone on a screen? Well, that's the journey we're about to take, following the path from raw electricity all the way to a diagnostic image.
The entire process hinges on one fundamental concept: a high-energy conversion. It all starts with electrical potential energy. I want you to think of it like a massive electrical hill, right? We create this hill by applying tens of thousands of volts between a negative cathode and a positive anode. This huge voltage forces electrons to race down that hill, converting all that potential energy into kinetic energy, the energy of pure motion. And then, when they finally reach the bottom of that hill and crash into the anode target, that kinetic energy is instantly transformed again, this time into electromagnetic radiation. And a tiny, tiny fraction of that radiation is the X-rays we actually need. So in this explainer, we're going to follow the life of a single electron, step by step. First, we'll start in the electron factory, which is where it's born. Then, we'll follow its journey across the void. We'll witness the violent impact and transformation when it smashes into its target. We'll explore how engineers are constantly taming the inferno of waste heat. We'll see how they're controlling the final beam. And finally, we'll look at the balance of power that makes this whole incredible process work. All right, so our journey begins. Before you can accelerate an electron, well, you need to have an electron. Or, more accurately, you need to convince one to leave its home atom. This all happens at the negative end of the tube, inside a component called the cathode assembly. This is our electron factory.
So inside the cathode, you'll find these tiny, tightly wound coils called filaments. Most modern tubes actually have two of them, a small one for fine detail images and a larger one for higher power scans. Now, when you pass a current through one of these filaments, its high electrical resistance causes it to glow white hot, kind of like the filament in an old incandescent light bulb. This intense heat really gets the atoms in the wire buzzing, and some of that thermal energy gets transferred to their outermost electrons. And this, right here, is where the magic really begins.
This whole process has a name. It's called thermionic emission. Let's break that down. It's pretty simple. Therm for heat, and ionic for ion, which is a charged particle. So it's literally emission by heat. The thermal energy becomes so great that the outer electrons get enough of a kick to just break free from their atoms entirely. They literally boil off the surface of the filament, forming this small, negatively charged cloud right around the wire. Physicists call this a space charge. And there they are, our free electrons, ready for their incredible journey. But why tungsten? Why is this one specific material always used? Well, it really comes down to three crucial properties. First, its ridiculously high melting point of over 3,400 degrees Celsius means it can glow white hot without, melting into a puddle. Second, it's ductile. That means you can draw it into a very thin wire and coil it up, which maximizes the surface area from which electrons can boil off. And more surface area means more electrons. And third, it has a high atomic number. This means it just has a ton of electrons in its outer shells that are just waiting to be liberated, which makes it a super efficient emitter. It's simply the perfect material for the job. Okay, so now we've got our cloud of free electrons, but a cloud isn't very useful, is it? We need a tight, focused beam. And that's the job of the focusing cup. This little metal cup surrounds the filament, and we give it a strong negative charge. Now, basic physics, right? Like charges repel. Since our electrons are also negative, the negatively charged cup literally herds them together. It squeezes that cloud through electrostatic repulsion and shapes it into a narrow, precise beam aimed directly at our target. It's basically an invisible magnetic lens.
So, our electron beam is now formed and aimed. The next stage of its life is a brief but incredibly violent acceleration as it starts its journey across the void.
This journey happens inside a sealed glass or metal envelope. And this envelope has three absolutely critical jobs. First and foremost, it maintains a near-perfect vacuum. This is totally non-negotiable. If there were any air molecules inside, our speeding electrons would just crash right into them, losing all their energy before they even reach the target. The vacuum ensures a clear, unobstructed runway. Second, the envelope itself, often made of Pyrex glass, is a fantastic electrical insulator that's essential for containing the tens of thousands of volts inside. And third, a specific part of the envelope, called the window, is made thinner or from a special material like beryllium to allow the useful X-ray beam to get out with minimal interference.
Okay, our electrons have been created, they've been focused, and they've just completed their high-speed flight across the vacuum. Now comes the moment of truth, the climax of their journey, a violent, instantaneous collision with the anode target. This is where the real transformation happens.
Propelled by that massive voltage, the electrons in our beam slam into the anode target at over half the speed of light. It's just an unbelievable amount of energy. The sudden, violent deceleration as they interact with the tungsten atoms of the target is what converts their kinetic energy into electromagnetic energy. But here's the crazy part, and it's absolutely crucial. Look at that pie chart. The process is incredibly inefficient. Over 99% of all that energy is converted into pure, useless, and incredibly destructive heat. Less than 1% becomes the diagnostic X-rays we actually want. You see, the X-ray tube isn't an X-ray machine that happens to produce heat. It's a furnace that produces a few X-rays as a tiny byproduct.
Now, this inefficiency creates a huge engineering problem. On one hand, we need a really large target area to spread out and absorb that intense heat. But for a sharp, clear image, we need the X-rays to come from a tiny pinpoint source. So how do you solve that contradiction? The solution is this really clever bit of geometry called the line focus principle. By beveling the anode target at an angle, the electron beam strikes a pretty large physical area. That's the actual focal spot, which is great for handling the heat. But because of that angle, when you look at it from the patient's perspective, the X-rays appear to be coming from a much smaller area, the effective focal spot. It's just a brilliant trick of geometry that gives you the best of both worlds.
That 99% waste heat is the single biggest enemy in X-ray tube design. If you don't manage it, the anode will simply vaporize in an instant. So, this next part of our story is all about thermodynamics and the absolutely ingenious solutions engineers have developed for taming that inferno.
Even with the line focus principle, if you kept hitting the exact same spot with that electron beam, it would melt, no question. So for pretty much anything other than very low-power applications like dental X-rays, the anode spins. I mean, look at the difference here. On the left, a stationary anode concentrates all that heat in one tiny spot. It just can't handle much power. But on the right, by spinning the anode disk at anywhere from 3,000 to 10,000 RPM, the electron beam is constantly hitting a fresh, cooler part of the target. So instead of a focal spot, you get a focal track, which spreads that thermal load over a much, much larger area. And that allows for far more powerful and longer exposures.
Okay, so spinning spreads the heat out, but how do you actually get the heat out of the tube? Well, it happens in three ways. First, and this is the most important one for the anode disk itself, is radiation. The glowing hot anode radiates infrared heat across the vacuum to the glass envelope. This is key because the vacuum prevents heat transfer by conduction or convection from the target surface. Second, some heat conducts down the molybdenum stem of the anode to the rotor. And third, all that heat is picked up by circulating oil in the tube housing, which then transfers it to the outer casing through convection.
Now let's look closer at the anode itself. It's not just one big chunk of metal. It's a sophisticated, layered defense system. The surface track, the part that gets hit, is a tungsten rhenium alloy. The rhenium is added to make the surface more durable and prevent it from cracking under all that repeated thermal stress. The body of the disc is made of lightweight stuff like molybdenum and graphite. Why? Well, a lighter disc is way easier to spin up to 10,000 RPM, which reduces the strain on the motor. And the stem that connects the disc to the rotor is made of molybdenum specifically because it's a bad heat conductor. This acts as a thermal barrier, preventing all that intense heat from reaching and destroying the delicate ball bearings of the rotor. Every single layer has a very specific purpose.
But this raises a pretty obvious question. How in the world do you spin a disk at 10,000 RPM inside a perfectly sealed vacuum without a physical axle breaking that seal? The answer is pure physics magic: electromagnetic induction. A set of copper coils, called the stator, sits outside the glass envelope. When electricity flows through them, they create a rotating magnetic field that passes right through the glass, completely untouched. This magnetic field then induces an electrical current in the copper rotor that's inside the vacuum. And the interaction of these magnetic fields forces the rotor to spin, basically chasing the external field. It's a motor with no physical connection. It is truly brilliant.
So, we've created electrons, we've accelerated them, we've smashed them into a spinning target, generated X-rays, and somehow managed all that incredible heat. We're almost there. The final stage is to shape the useful X-ray beam and, of course, make sure the whole system is safe.
You know, a common misconception is that X-rays just shoot out in a neat little beam. They don't. When the electrons hit the target, X-rays are produced isotropically. That means in all directions, a full 360 degrees. Most of this is stray radiation that we don't want, and that's why the entire tube assembly is placed inside this heavy, lead-lined metal housing. The lead absorbs all that stray radiation, which protects the staff and the patient from any unnecessary exposure. The housing is also filled with a special dielectric oil that does two things. One, it's a great electrical insulator to prevent high-voltage arcing, and two, it's the final link in our cooling chain, absorbing heat from the tube and carrying it out to the casing. Only a small window or port lets the useful, shaped beam exit towards the patient.
So let's bring it all together now. From a simple, glowing filament to a controlled diagnostic beam, the X-ray tube is this incredible orchestra of physics principles and clever engineering solutions, all working in perfect harmony. It really is the true balance of power.
This table really just summarizes our entire journey, doesn't it? You've got the tungsten filament using thermionic emission to create electrons, the focusing cup uses electrostatic repulsion to steer them, the tungsten rhenium target track uses the violent deceleration of electrons to make the X-rays, the molybdenum stem uses port conductivity as a thermal insulator, the beryllium window uses low attenuation for an easy exit path, and the copper and iron rotor/stator pair uses electromagnetic induction to create rotation. Every single part is a direct, practical application of a core physics principle.
So the next time you look at an X-ray or a CT scan, you're not just looking at a picture, you are looking at the end result of this incredible, violent, and yet perfectly controlled process. This is a device that orchestrates a collision of subatomic particles at half the speed of light, all while containing lethal voltages and managing catastrophic amounts of waste heat. Understanding these components is what allows radiographers and physicists to control image quality, to manage the life of the tube, and above all, to optimize patient safety.
It really makes you think, doesn't it? We have this device of violent extremes: extreme heat, extreme speed, extreme voltage, and it's all perfectly balanced to create something so delicate and so diagnostic. It just makes you wonder, what other technologies that we rely on every single day are hiding such an incredible, hidden world of physics right beneath the surface?